Gold extraction is an industry of extreme ratios. Securing a few ounces of metal requires pulverizing tons of ore, leaving behind a massive volume of ground rock that requires specialized containment. Every modern tailings storage facility, or TSF, functions as a highly engineered active biogeochemical reactor. The input feeding this system is a continuous slurry, a mixture of finely ground quartz and sulfide rock suspended in process water at exactly 45% solids by weight. To manage this material, the facility must execute 3 absolute mandates: secure the solids physically, neutralize the chemical hazards, and recover process water for recycling. Managing this flow requires treating the storage facility as a continuous flow machine. Neglecting any single mandate guarantees a catastrophic environmental failure. To understand how the system prevents that failure, we can follow the physical flow of the material from the plant to the central pool. A top-down map of the facility reveals 4 distinct operational nodes: the spigot, the chemical circuit, the decant pool, and the structural dam core. The journey begins at the first node, where high-pressure slurry exits the pipeline and enters the open environment. As the material moves through these nodes, engineers must combat physical hazards like liquefaction and chemical hazards like acid drainage in real time. Because the TSF is a closed loop, an unresolved hazard at the start of the journey creates a mathematical certainty of a structural breach at the end. The slurry travels from the mill through heavy-duty HDPE pipelines capable of handling the 45% solid concentration. Automated pressure transducers along the line monitor fluid dynamics, allowing operators to detect internal blockages before they lead to a pipeline failure. This cross-section illustrates rotational subaerial spigoting. The slurry discharges, heavier, coarse solids rapidly drop out of suspension, accumulating against the dam wall to form dense, stable beaches. The lighter liquid flows inward, collecting in a central decant pool, isolated from the outer crest. Keeping the water pool away from the dam crest prevents soil saturation and internal erosion within the earthen wall. The spatial geometry of where these solids and liquids settle acts as the facility's primary, non-mechanical defense against structural collapse. While gravity manages the solids, the slurry water contains residual cyanide from the gold extraction process that must be addressed. In the cyanide destruction circuit, an SO2 air mixture and copper sulfate catalyze a reaction that breaks down these chemical compounds. This circuit maintains the weak acid dissociable cyanide below a strict limit of 50 mg per liter at the point of discharge. The central decant pool serves a secondary role as a massive, passive clarifying basin. The pool utilizes continuous solar UV radiation to break down and degrade any remaining trace cyanide compounds over time. This decant pool is a continuous, passive chemical reactor working in tandem with the upstream active catalysis. At the center of the decant pool, floating pump barges manage the water volume. These barges are capable of recovering 85 to 90% of the total process water. This water returns to the mill's comminution circuit for immediate reuse in the grinding process. This recycling loop eliminates the need for any external effluent discharge into local watersheds. This reclamation meets the economic demands of the plant while simultaneously reducing the hydraulic pressure on the tailings dam. The final critical barrier is the dam wall itself, which must constantly support millions of tons of material. Internal piezometers are installed deep within the dam core to monitor the structure from the inside. They track invisible piezometric pressure levels, alerting engineers to water buildup. On the crest, automated systems monitor the freeboard, the distance between the water level and the dam's top. This gap must be large enough to absorb a sudden 1-in-100-year flood event without overtopping. Outside the structure, downstream seepage interception wells and pumps provide a final line of defense. Engineers conduct routine geochemical testing on this groundwater to detect any signs of escaping acid rock drainage. The structural safety of the facility relies on this real-time automated sensor network to make invisible geotechnical threats actionable. Detoxification, spatial deposition, and constant monitoring operate in tandem to maintain the facility's equilibrium. The reclamation barges serve as both the financial lifeblood of the mill and the primary geotechnical relief valve for the dam. Modern tailings management replaces the unmonitored waste dumps of the past with a strict, data-driven engineering reality. Rigorous engineering protocols ensure this abrasive, chemically active waste stream remains a secure, predictable, closed-loop machine.